Imagine supporting astronauts on the moon with a fleet of intelligent robotic assistants. Our project, developed for the NASA Lunabotics competition, focuses on designing the control system that powers these robotic platforms. We have created a modular architecture composed of a signal processing unit and a power distribution system, allowing a single design to support multiple rover functions, from exploration and sample collection to transportation and system monitoring. We have prioritized modularity, reliability, and efficiency. In essence, we're just not creating a rover. We are developing a foundation for the next generation of lunar robotics.
In Senior Design 1, the team evaluated multiple control system architectures for the Lunabotics rover, including an Arduino-based controller and a TI-based controller. The selection criteria included reliability, ease of integration, computational capability, power efficiency, and thermal stability. Each criterion was weighted based on project priorities, with reliability and computational capability receiving the highest importance. The Arduino-based controller was selected due to its ease of integration, faster development time, and proven reliability within the team's existing system. During Senior Design 2, the concept evolved as the team began evaluating TI controller for improved real-time motor control and performance. However, the Arduino-based system remains in the current implementation, while the TI controller is being considered as a future upgrade to enhance system capabilities.
Next, we will go over the end product description of the project. Now, as mentioned before, we are a robotics team working on a lunar rover for the NASA Lunabotics competition. Regarding this, we have a number of inputs, outputs, signal flow, and signal processing that I will be going over. As far as the inputs that are required for this project, we have a number of motors that need to be controlled on the robot. So we have the capabilities to send controller data from one end of a Wi-Fi connection to the other. We have a computer mounted onto the rover, which will be able to receive data from a controller and be able to interpret that data to be used later on to control the motors. As far as outputs coming out from the robot, we have a camera mounted on the robot that will be used to send data back to the controller, to the operator, to be able to know what the robot should be doing next. Going into how this signal will be interpreted, we have a Raspberry Pi mounted onto the rover that will obtain the controller data and send it out to the motors, as mentioned previously. And we also have an Arduino mounted that will get that signal from the controller and be able to interpret that, sending it off to the motor drivers to be used later on, finally, to move the robot, of course. And activities that are required by the competition, such as picking up regolith with the scooper and being able to vibrate that to obtain it easier. Shown here is a demo of the activation system for the robot, functioning as it should, being controlled with the electrical box and the battery connection. As you can see here, it can go up, down, and also pivot on an axis and be able to go at different angles. It's also able to descend quickly, and here we have the electrical box controlling the motors of the robot.
So as you can see in this video, I'm using a joystick to control the robot. You can also see an LED light turning on and off, which shows the exact response that the rover will have. As I push the joystick forward, the robot moves faster, and then as you can see here, it comes to a complete stop.